U.S. Naval Academy from Annapolis, Maryland. As you probably read already, he teaches in the Department of Mathematics and Oceanography down there, and has probably a very different student body than we have here, except with a few exceptions, I guess. Okay, so yeah, I guess you talked about busy schedules. These students have a lot more on their plates than you folks do. So enjoy all the luxury you have, and spend more time studying. So in 1989, Ray earned his PhD in metrology from Penn State University and specialized in optics of the atmosphere, which, of course, anyone who's doing remote sensing was going to be very interested in that. His research in atmospheric optics and radio transfer have been supported by NSF grants, and he's published a number of papers, many of them in applied optics. And I'm particularly jealous of his 2004 paper that was published with Michael Berry, who's world-renowned theoretical physicist who studies all kinds of interesting things with polarization, and used some of Ray's work to look at the sky and find some interesting singularities even in the sky. So with that,
right.
Welcome, Ray. Thanks.
Very much. Thanks very much, Professor Swartzlander, and I'd also like to thank Professor Kanan, who made the initial invitation, and the Center for Imaging Science for having a strange bird come and talk to him about a topic that no one could possibly be interested in, except, yes, yours truly. What could be more obvious than the clear blue daytime sky, right? I mean, out of the blue, there's nothing there, except, why is it blue? Now, let's just review, if we could have the lights down a little bit. Let's just take a look at this halcyon rural scene in western Pennsylvania. You'll notice that as you get a little closer to the horizon, there's a change in the color. What happens to the color there? It gets a little bit less saturated. It's a little more white. This white band along the horizon is nothing unique to rural Pennsylvania or rural New York for that matter. It's an intrinsic part of the clear sky. So we have to be able to explain that in addition to, and lest I forget the founders of the feast, my friends and colleagues at the National Science Foundation and the Atmospheric and Geospace Sciences Division have been kind enough, or perhaps the word is incautious enough, to give me a number of grants. So there's our picture. There's our standard for what's going on. Why is the sky blue? Any self-respecting meteorologist, and I would say any imaging scientist, needs to know the answer to this person in the street question. Molecules are smaller than wavelengths of lambda visible light. Okay, we're done. Thank you very much. That was the shortest lecture ever. Well, that's the succinct answer, but it's not very satisfying. So let's go back to basics and look at William Strutt's original arguments, later Lord Rayleigh. No relation, by the way. My parents were not possessed of a strange sense of humor. If that were the case, it would also apply to my father, who was Raymond Lee Sr. Who knows? In 1871, he makes two arguments in parallel about why the sky is blue. First, there's dimensional analysis, in which Rayleigh says, well, a particle that is much smaller than the wavelengths of light, with a radius r sub p, say less than a tenth the wavelength, will have scattering that is proportional to its volume v, because the particle's constituent atoms scatter in phase, since they're all lit up at any instant by about the same part of the wavelength. Okay? Second, the scattered light's amplitude, E sub s, is proportional to v, and also to the input signal, E sub I, the incident light's amplitude. Now, energy conservation requires the scattered irradiance, E sub s squared, to decrease with distance as 1 over r squared, and the scattered amplitudes as 1 over r, which means that the ratio of the scattered to incident irradiances is proportional to v squared over r squared, and dimensional balance requires that we have another factor of length in there, 1 over length to the 4th power, for which 1 over lambda to the 4th is a logical candidate. More rigorously, Rayleigh says, or Strutt says, using in modern parlance light speed c, angular frequency omega, 2 pi c over lambda, time t, phase angle delta, getting tired already? Maximum amplitude E naught, the time dependence of the incident amplitude is proportional to the sine of omega t minus delta. Right. The acceleration of the scattered waves then, E sub s, is proportional to the second partial of E sub I with respect to time, or proportional to minus omega squared, which of course is proportional to 1 over lambda squared. But it's not just E sub s we need, it's the ratio of E sub s to E sub I squared. So the 1 over lambda squared itself is squared, and from another tack we get 1 over lambda to the 4th. Scattered skylight has a pronounced blue bias. So smart guy, if it's better scattering at shorter wavelengths, how come the guy is not violet instead of blue, and why is it not the same color everywhere if there's this universal law? Several reasons. Perception and physics together conspire to give us the beautiful blue sky that we know. The photopic sensitivity function is about 3,500 times greater at typical blue sky wavelengths of 480 nanometers than it is at violet wavelengths. Second, skylight's source of sunlight in sunlight has much less energy at violet wavelengths than it does at typical blue sky wavelengths. And yet there's another contributing factor. Skylight isn't light of a single wavelength, but a continuum of many wavelengths that are spectrally integrated by our visual systems into 3 broad bandwidth signals. And so that smooths out spectral extremes like that which you see for the lambda to the -4 relationship here at the very shortest wavelengths. And then finally, that pesky white horizon and the color gradients of blue that merge seamlessly with it require us to consider how multiple scattering transforms the intrinsically lambda to the -4 bias of single scattering into a range of colors. So here we've got our great Cyclops eye admiring the sky, which we've converted into an atmosphere that has uniform density and finite thickness. Completely the opposite of the real atmosphere, but that's the least of the horrors that we are about to commit here. It works and it's defensible. As you look closer to the horizon, say, along direction A, light coming to you from that direction has at each point along the illuminated path undergone identical Rayleigh scattering, just as it has when you look higher in the sky. But what's the chief difference between these two paths? This path is a lot longer, and so if you have a longer path with more contributions coming towards you, what's going to be the nature of that signal? It's going to be brighter, more contributions. What's going to happen to the most distant contributions? Those are going to run the gauntlet to make it to your eye, and each of those at every point along the way when they encounter a molecule or a small aerosol particle are going to undergo the same blue biased scattering, that is removal of blue from the beam. So what do you get? You get more contributions to the light in that direction, with the most distant ones now reddened and the closer ones to you near your eye still showing their distinctive blue bias. So you get a brighter, whiter signal as you look toward the horizon. And that happens very quickly. Even if we replace this slab atmosphere with a spherical shell atmosphere, you get the same results. Okay. I've been talking about molecular scattering. You can also have scattering by aerosols, or what we call collectively haze, which is often defined by scattering consequences rather than by its constituents. the consequences, as you see in this photograph of an island in the Gulf of St. Lawrence, are that as physical path lengths to an object increase, the total amount of scattering increases, and the signal gets brighter. What happens to that brighter signal? It reduces the brightness differences that are inherent at the surface, and so you have reduced contrast. Now, this differs only by degree, not kind, from clear sky air light, and which is the whitening of the horizon, and it also contributes to decreased infrared albedo in the upper troposphere. The constituents typical for this area and for Annapolis are hygroscopic or condensation encouraging aerosols such as sea salts and ammonium sulfate, tropospheric dust, small particles, and particles and photochemicals, smog, which I fear we suffer more than you do. And for really spectacular sky colors, you can have volcanic ash or sulfuric acid droplets in the stratosphere. Everybody needs an equipment picture, right? Mine is not much to brag about. Here it is set up in my backyard on a tripod with 3 degrees of adjustable freedom, a Resonon Pica 2 imaging spectrometer on a rotation stage. There's the stage, the spectrometer, a monochrome camera with a diffraction rating in it, is moved line by line by this sepper motor in the stage, with the whole thing controlled by this MacBook Pro laptop, which in fact is showing you this presentation, fittingly enough. Now, to quantify the effects of haze, we use the aerosol optical depth, tau air sub lambda. It's measured around the world near the U.S. Naval Academy, USNA. We also have a couple of sites in what is called the Aerosol Robotic Network, or AeroNet. And here are a bunch of spectra of tau air, going from violet wavelengths down to the beginnings of the near infrared. And on hazy days, you can see that each one of these curves, measured at a few discrete wavelengths divisible, has a distinctly higher value, and this is a dimensionless quantity, than it does on clear sky days. You convert those discrete measurements to a continuous function using this power law with angstrom coefficient alpha, if this were a collection of molecules, alpha would be equal to 4, minus 4. But for aerosols, it's about minus 1.5 plus or minus 0.4 standard deviation. You start to notice haze when at the shortest wavelengths, the amount of the normal or vertical aerosol optical depth exceeds 0.2. And here are a couple of RGB images calculated from hyperspectral data. You look at the spectrum at each pixel in one of these data sets, calculate a CIS chromaticity from it, and from that you calculate a device-dependent red, green, blue signal, which you then paste into your picture. So what do we see on the low humidity, low aerosol day, when the sun at H0 or elevation of 30 degrees and at 90 degrees from the sun? What do we see on such a day? That's a fairly low aerosol amount. Nice blue color gradation of the kind that we are used to. Now, what does this phi rel equal 90 degrees mean? You're looking at right angles to the sun. So if the projector is the sun, you're looking over here. Now, on this hazy day that is paired with much higher aerosol total, now phi rel is 270 degrees. Oh my goodness, how are those comparable? Well, it's 2 is 90 degrees from the sun. It's just in the opposite sense of rotation. So for a single scattering, those two angles combined with nearly the same sun elevation are going to give you the same scattering geometry. But these two images look very different. How do they differ? well, the white horizon is a lot more noticeable, and you can start, the sun is off here to the left, you can start to see a brightening in that direction, which is due to your increasing proximity, the decreasing angle between where you're looking and the sun. No such clue is really evident here. Now, I'm going to show you a number of CIE colorimetric diagrams, for those of you not familiar with them. It's a rectangular coordinate system in which we take spectral data and map it into these two coordinates. Here I'm using the 1976 U prime, V prime system. This is roughly the blue to blue-green axis here, and this is roughly the blue to red axis along the horizontal. So, as I've also included here as a landmark, this curve of the black body, or Planckian radiator's colors, ranging from about 5,700 Kelvin down up to 2,700 Kelvin. Bluer colors are that way, and redder colors are this way. Keep that in mind. Hang on tenaciously to that thought if you're not familiar with such diagrams. So, what I have done here is to scan up from the horizon and take an average over a 4-degree wide band, which is about this wide in each one of these images, and average those chromaticities to get a meridional, or along a sky meridian, profile from horizon to the top of the image, which is about 45 degrees. And that's what you see here. For the hazy sky day, the red curve starts near the horizon, and there's 10 degrees elevation. H is the elevation angle of where you're looking, the view elevation angle H. And at 39 degrees, this curve starts to turn around, and there it stops at 46 degrees. Not much motion when you get up here above the horizon. The color transitions are very, very slow and small. For a sense of perceptual scale, I've also included something called the McAdam just noticeable difference here. The length of this blue line is the smallest color difference that if you were comparing these two simultaneously, you can't, they're on different days, but if you were comparing them simultaneously, you would just be able to tell the two colors apart. Here on the haze-free day, a much lower aerosol optical depth, you get a wider range of colors, a larger color gamut than you do for the hazy sky. That makes sense. You saw a compressed color gamut in the hazy sky. It was whiter. It wasn't the blues were as good, and the white horizon was wider. In both cases, sky blueness, or the correlated color temperature, increases with increasing view elevation angle H. And we get this curious kind of hook here at about 40 degrees elevation. And it's a curious thing because the back of the envelope statement is, well, as you look farther from the horizon, it just gets bluer. There should never be any change. Because you're reducing the amount of multiple scattering, you're reducing the contamination of the Rayleigh signal, and it should just keep getting bluer as you look farther away from the horizon up toward the zenith. Except the atmosphere and reality disagree with us. We have to explain. For a different pair of clear versus hazy skies, oh, by the way, we think we got this all sorted out. This kind of makes sense that on the hazy sky day, the entire curve is shifted which way? Toward the Planckian locus. That's the region, part of which is the sort of achromatic region of the CIE diagram, the color-free region. Okay, that sky was whiter overall, so that makes sense. So I got it. On hazy days, the chromaticities are all shifted toward the neutral axis, the Planckian locus, except when they're not. Okay, here we have two different days. Again, the day with no haze, the dashed green line here, has a wider gamut of colors. It now starts to show evidence of a hook here at 45 degrees. And it's displaced toward higher color temperatures, bluer colors, than its hazy sky counterpart with a smaller gamut. But it's at the same distance from the Planckian locus, which is hard to explain. Now, the fact that this behaves consistently, the low or no haze day, is not surprising. We're getting close to a molecular atmosphere. There's only one possibility for the molecular atmosphere in a particular direction with a particular sun elevation. So the fact that it's sort of stable and stays put is not surprising. Predicting how the haze chromaticities would jump around from day to day is less obvious. Switch venues. Go back to Western Pennsylvania. I own a farm there. That's what this is all about. We got no foul urban contaminants. We're out here in the middle of nowhere with beautiful blue sky. Again, the sun elevation is about 30 degrees. We're looking at right angles to the sun. Magnificent color gradation all the way up to, again, about 45 degrees at the top. And if we turn 90 degrees and look opposite the sun, notice what we've got. The blue is even deeper, even purer in that direction, and that's not surprising because the purest blues will occur in a multiple scattering real atmosphere at a combined elevation and azimuth angle of about 90 degrees. And that you find over about here for this sun elevation, not here when you're getting closer to this. So there is one supposition, perhaps the kind of aerosols, here a coastal environment, here a rural environment, cause these different kinds of chromaticity curves. But these bloody hooks there that aren't supposed to be there, what are those about? Well, it turns out, after a lot of head scratching and some modeling, this is a signature of aerosols. It varies in elevation angle, but there is some increased reddening by aerosols as you look closer to the zenith, and that's combined with increased bluing as you reduce the optical depth up toward the zenith. So the blue and the red are going in opposite directions, and you get a stationary point here in the color. Turn around as a consequence of this competing reddening and bluing inputs, possible only in an aerosol atmosphere. And if you're thinking, well, I know what's going on here, this rural curve with all those trees and grass, that's going to shove the entire curve toward the green. Well, unfortunately, green is up that way. There are lots of clever ideas or intuitively obvious ideas that just don't happen. So it's difficult to sort out. Now, when you go to vacation in Bar Harbor, Maine, the first thing to do is to climb Cadillac Mountain and take your imaging spectrometer with you and take now a full-fledged proper scan from the horizon all the way up to the zenith. And now the hooks are very obvious. Two scans taken the same day. One at 90 degrees relative azimuth, one opposite the sun at 180 degrees relative azimuth. The hooks are very obvious. And this is, again, the signature of the competing effects of reddening by aerosols as you get closer to the zenith and increased bluing due to reduced optical depth. So you get the bluest skylight occurring at very different elevation angles in these two directions. Here it's 38 degrees. And there it's about 48 degrees. Now, another way of looking at haze's effects on clear sky colors is, I love appallingly simple ideas, and this is another one of them. For a given sun elevation and a given viewing direction, h and relative azimuth, simply take the ratio, wavelength by wavelength, of the spectral radiances in a hazy sky to those in a clear sky. So what you'll get, in effect, is a spectral transfer function for that particular combination on two different days. Here we have a clear day, September 10th, 2012 versus August 29th, a hazy day, and there's another hazy day there, August 31st. What do you see close to the horizon? There's a local minimum in this transfer function, meaning that as a spectral filter, if you will, the effect of the hazy atmosphere is to create a local minimum near about 480 nanometers in its effects on skylight. When you get to the transfer function equal to 1 throughout the spectrum, there's no difference at all. That sky would be identical to the one that you're using as your denominator here, those radiances. So that's the pattern, and you have a local maximum in turn at about 680 nanometers. Now, shift your gaze up 15 degrees to 20 degrees elevation, same relative azimuth. That local minimum in the blue disappears. And before we get too excited here, remember, this ratio of 1 means that the haze has absolutely no effect. Well, here it's having some effect, but that really visually simply results in desaturating skylight blueness at this particular elevation angle and scattering angle, the combined elevation and azimuth angles. And you get a much smaller shift in the red curve because that day the haze was less pronounced. Its signal is closer spectrally to 1 at every wavelength on that day. And the fun never ends here. If you look at 90 degrees from the sun, here is the summary of what you get. A slight bluish bias at low elevation angles disappears, and there it is at 5 degrees elevation. It starts to disappear, that local minimum, and by the time you get 20 degrees above the horizon, there's no evidence of it. And you have near linear increases for wavelengths less than 680 nanometers at higher elevations, and then decreases or roll off at longer wavelengths. So the net result is tropospheric haze often causes an orangish shift in clear sky colors except right near the horizon, where you get this purplish shift, a minimum in blue and a maximum in red. That's true for 90 degrees relative azimuth, and it's also true when you look opposite the sun. That local minimum in blue, which gives you a purplish color shift near the horizon, disappears as you look upward. Now, instead of doing this, that was results from a narrow field of view spectrometer, a 1 degree field of view. It's a 1 pixel scale that you saw back there. Let's do it for a hyperspectral pair of images. Yeah? Do it pixel by pixel. Divide at each pixel in, I don't know how many thousands there are here, but at each pixel divide the spectra, and then do lots of smoothing because it's a nasty, horrible looking thing when you're done, and show us the map. Visually, what is the result? Mostly an orange shift introduced into sky color by haze or aerosol, except right near the horizon where the shift is purplish. And that's true both at right angles to the sun and opposite to the sun. Oh, I'm tired of talking about daylight. I want to talk about twilight. Or better. Twilight is one of the great underappreciated and understudied phenomena, despite the tons of things that have been written about it. And there's a reason for that. And the reason is it happens so quickly. If you've got half an hour to do all your research, you're out of business very soon. So the way I solve that problem is to ask for a window seat, please, whenever I fly. You should too. Pay no attention to the in-flight movie. Pay no attention to what's on your smartphone or your tablet. Look out the window. You will be amazed at what you see. And if you get a chance, sit on the anti-solar side of the aircraft, that is opposite the sun, when you have a chance of going through twilight. Because there you'll see the anti-solar sky, which is what we do here at an elevation of about 10 kilometers. And the sky color features that you see there, such as the reddish or rose-colored anti-twilight arch, I'll abbreviate it later as ATA. This is also called the belt of Venus, for reasons that aren't particularly obvious, but I'll get to that. And below that is the dark segment, or Earth's shadow. This is not strictly correct, but conveys the flavor of what's going on. This is the last sunlit bit of the atmosphere. The sun is, you have direct reddened sunlight here, that's why the color, and below here, this is not the ground. This is the atmosphere indirectly lit and sending its signal back to you. You can see the same thing from the ground. Here's a fisheye picture taken at the Naval Academy. The sun's about 2.5 degrees below the horizon. There is the sun below the horizon over there. And here is the anti-twilight arch, or ATA. I'll use that again and again. And beneath it, closer to the horizon, is the dark segment. You notice how this band of reddish light extends all the way around. Sort of like a belt or girdle. That's why the name Belt of Venus. It mostly persists in astronomical literature these days, but that's where that name comes from, most likely. So what you're looking at here is the combined effects of molecular and aerosol scattering. How do aerosols in this very different lighting regime, such as soil particles, sulfates, and nitrate solution droplets, affect twilight colors? They add to the normal or vertical optical depth, which for molecules, of course, is our old friend lambda to the -4, at a more modest rate of lambda to the -1.6 plus or minus 0.4, the number that I mentioned before. This is one standard deviation in the angstrom coefficient there. So which is more effective at making blue? Lambda to the -4 or lambda to the -1.6? Well, clearly this is a bigger, badder number, and should give you better blues. But what's one of the things that we constantly hear is that if you want the most spectacular sunsets, you got to throw some junk up into the atmosphere. You got to have some aerosol up there. So aerosols redden direct sunlight and the near horizon solar sky in the direction of the sun, including the setting sun, and may perhaps redden the anti-solar sky like the alpenglow or mountain glow. If you want to see a spectacular alpenglow photo, this mountain's white, by the way, that's its reflectance signature, but you got to have a really aerosol-laden atmosphere to give you a nice Bafo red sunset to give this beautiful orange. Maybe that's what's going on with aerosol. Might they redden anti-solar twilight colors too? This is the anti-solar direction, this sunlit mountain. And here are some 3 cases that I've measured for twilight aerosol optical depths: a heavy aerosol day, a moderate one, and a minimal aerosol day. Using the same techniques I did during the day, I now construct from hyperspectral scans made in the horizontal direction these 180-degree wide strip images of twilight. Here is the minimum aerosol day. Well, it's a nice kind of anti-twilight arch there with the dark segment beneath it. Well, it's not so good here when we shift to the intermediate case, and there's not much there at all when you get the atmosphere all loaded up. And here's what you see on the CIE diagram. Remember, red is that away and blue is that away. Here is the minimum aerosol case in blue. You get this large excursion, meaning a red anti-twilight arch. And on the intervening or moderate aerosol day, it's not quite as good, and it's shrunk even more with the maximum aerosol amount. So what's the moral there? It looks like if you keep taking out aerosol, you get better and better anti-solar colors. I incautiously published a paper a few years ago which said, well, clearly there's some lower limit. We have to stop somewhere because everyone knows you need, to get better colors in twilight, you need more aerosol. Foolishness of youth. There we are. I'll show you how that works. A Monte Carlo model called MISTIC, which is proven to be pretty robust, it's been around for about 20 years, suggests that any amount of tropospheric aerosol is going to reduce the gamut or spread and the vividness of surface-based anti-twilight colors. Here's the minimum aerosol amount that we measured, plus some ozone absorption, cranked into the MISTIC model, and that's the result. Oh, nice. There's the reddest anti-solar color, 6.1 degrees above the horizon. But if we take out all the aerosol, something we can't do in reality, guess what happens? You get even better reds. Time for a second paper. Skipping over as delicately as you can the fact that you blew it the first time. You made a reasonable supposition. It was just, here's a technical term, wrong. What's the best anti-solar colors? No aerosol at all. So there it is. Model A is a purely molecular atmosphere. Now, you'd like to see some of this in reality. How can we make anti-solar colors that we could measure and photograph even better? MISTIC suggests moving to the lower stratosphere. I have a solution for that. It's called a window seat, please. Okay? Here we have the best surface anti-solar colors, the blue line here. And remember, farther that way is redder. MISTIC says, well, if you go up 10 kilometers and keep the aerosol and the ozone, you'll get even better, redder colors. And oh, by the way, remove all of the aerosol if you want to get the best possible color. And here we are above the Yukon. Sun's about 3 degrees below the horizon. I photographed in the anti-solar direction here. Yeah, you get some sense of that. Now the anti-twilight colors that are produced by the total optical path along these slant paths is less than when you're at the surface. It still has to go through the entire troposphere once. The tangent or grazing rays at the surface shine through the entire atmosphere, light up this part of the stratosphere, but then there's an aerosol-free or minimum aerosol trip back to you as you fly along here far above the troposphere or near the top of the troposphere. So in other words, the backscattering paths are essentially free of aerosol at that elevation. And here's the result. But here's a fun fact. Now this is colorimetrically calibrated images. They're so fussy about my bringing the scanning spectrometer on board the aircraft. I don't know what it is. My seat may complain, so I had to use photographs. And you can colorimetrically calibrate those with the camera of known performance. And here's what you get. This is from Wyoming, the same sun elevation about as this picture you saw in Yukon. But those better reds actually aren't as red as you might think because the whole thing has been shifted here to higher color temperature at the end, the very end of the Planckian locus. So it's more complicated than we thought. Now, a couple of model results and I'll let you go. Let's look at the reddest part of the twilight atmosphere through the belt of Venus, or in the anti-solar direction, the anti-twilight arch. So along this red band, I'm going to simulate colors through the reddest part of the belt of Venus. And here are results from the MISTIC Monte Carlo model, in which I'm drawing these strip diagrams from the anti-solar direction. The sun is about 1.5 degrees below the horizon. I'm at the Earth's surface. Here are the colors that the best reds that you would get along that curved path, almost parallel to the horizon, for a purely molecular atmosphere. Okay, that doesn't look too bad. A nice red in the anti-solar direction. Now let's crank in the actual observed minimum aerosol case that I showed you earlier. Ooh, the red isn't nearly so good, but hey, the sunset's horizon, that's better, that's better. Yeah, I know, aerosols are good, more aerosols. Oh, there's nothing here. The anti-twilight arch has disappeared. And things don't look so good over here either. What's happening? If you increase multiple scattering enough, what do you get? Mud. You get mud if you increase enough, you have enough scattering going on. Photons rattle around in there and spectral selectivity goes down the drain. And so the corresponding colorimetric curve in a purely molecular atmosphere can do this seemingly contradictory thing of giving you both a redder anti-twilight arch and a less red anti-solar sky. So, the blue dashed curve is the molecular case with ozone absorption. The minimum aerosol case that we talked about earlier is the red, and the green is the maximum aerosol case. So, the dashed line is the molecular atmosphere. It's not quite as red as the minimum aerosol case in the solar direction, relative azimuth at 0 degrees at the horizon. But as we come back here toward the anti-solar direction, look, it's less blue, otherwise known as more red, than the minimum aerosol case. And as for our scheme to make everything better by adding still more aerosol, we get a terrible sunset color and even bluer anti-solar colors. We kill both solar and anti-solar twilight colors. But the direction we're most likely to think of, and if you don't think of this, get in the habit of doing so, is what's called the principal plane direction. The principal plane is the thing defined by you. You know, in an age of selfies, why not start with yourself? You, the zenith, and the sun, wherever it is, those 3 points define the principal plane, a vertical plane that passes through you in the zenith. It's the plane of scattering symmetry, or single scattering. So that's the plane that we're going to follow and simulate colors in from the red solar direction to the rose-colored anti-solar direction. And here's what happens. Again, there's the anti-solar horizon. Now we're looking up toward the zenith and back over. We're careful not to fall over. And you look back here toward the sunset. There's the purely molecular case. Whoa, look at that. That's very nice, beautiful anti-solar colors. Great zenith, not so good solar colors. We improve the sunset sky at the expense of the anti-twilight arch if we add a little bit of aerosol. And as far as glopping it on there, the maximum aerosol amount does violence both to the sunset colors. Now they start to get muddy and essentially wipes out that anti-solar display. So the same kind of patterns emerge here. The reddest anti-twilight arch occurs in the molecular atmosphere, but the reddest solar sky seems to require some just so amount of aerosol. I don't know what it is. We have to keep tinkering to find out what the best aerosol amount is to do that. But here's the, this minimum aerosol case clearly is redder in the solar direction, and yet it produces a less red anti-solar. And finally, what's going on with sky brightness? This is a logarithmic plot of luminance versus scattering angle. Think of scattering angle here as angle from the horizon in the direction of the sun up through the zenith and then back over your head to look at the anti-solar sky. So in the maximum aerosol case, you have reduced and wider local maximum in the solar sky and the anti-solar sky. And the brightest solar sky is that, again, that just so amount of aerosol, whereas the molecular sky gives you a less bright solar horizon, but a much brighter and, as we've seen already, more colorful anti-twilight arch and dark segment. So, what do we know about haze and its effects on clear daytime skies? Well, of course, haze merely desaturates clear sky colors. You just haven't known the details until now. Sometimes what you don't know is a useful thing to eliminate. Even if you can't explain it, at least knowing what the nature of the problem is a good start. Some hazy sky chromaticity curves along the sky meridians are shifted toward the Planckian locus, while others are shifted redward toward lower CCTs. And this doesn't seem to depend solely on aerosol optical depth. At higher elevation angles, the hazy anti-solar sky is relatively more bluish than light from the same sky at right angles to the sun, even as haze decreases the overall color gamut and range, delta L, of luminances. So at our measurement sites, the haze transfer function gives us bluish biases near the horizon, perhaps from aerosol multiple scattering over those longest land paths, and reddening from about 680 to 730 nanometers at most elevation angles, and very few local minima, such as would be caused by aerosol absorption, invisible. And a second order scattering model shows us that those funny hooks we see are caused by aerosol scattering that reddens skylight slightly as you look toward the sun, competing with reduced multiple scattering at higher elevation angles. We're looking up toward the zenith that makes skylight bluer in that direction. And the last bit of content, what do we say about the anti-solar twilight sky? Well, there is any amount of tropospheric aerosol added to the atmosphere is going to make for less vivid anti-twilight arch colors and reduced color gamut. But small amounts are going to make the solar sky redder and more vivid. So the one-sentence summary is, in radiative transfer accounting terms, a little aerosol scattering reddens the solar sky at the anti-twilight arch's expense. And adding more aerosol at some unknown mystical minimum amount is going to desaturate and make bluer both the anti-twilight arch and the solar sky. We come closest to seeing the truly molecular atmosphere when we climb on that plane, and we do what? We ask for a window seat to look out the window at twilight, or better. You can do that less dramatically from a mountaintop, although with more effort. And the modeled twilight luminances as a function of scattering angle psi respond plausibly to what happens to aerosols addition. Their strong forward scattering increases the solar sky luminance, but decreases the anti-solar sky luminance. But adding too many aerosols plays havoc, wipes out both of those. And what color is the nighttime clear sky? Well, it's blue, of course, except you have to be very patient. Thank you.
Okay, well, I think you never look at the sky the same way again.
Or maybe with fear and trepidation.
Questions, please.
And by the way, if you're not troubled by this picture, see me. You should be troubled by it briefly. But if you've been paying attention, you won't be for long. Those are star tracks. And that's the time exposure.
Dimitri.
So, given your own recent experience with these simulations and multiple scattering and everything like that, at what point, or can we ever say when it's time to stop pretending we live on a flat Earth and start using actual 3D codes?
One of the big selling points for me with this MYSTIC model is it uses a spherical shell atmosphere.
Yeah.
I know that I believe that ModTran has been upgraded to include a spherical shell atmosphere option, but just as a giggle, I showed what ModTran, it would give you answers. It would produce numbers and chromaticities, and it was nonsense. Because the problem with a plain parallel atmosphere, which was the original ModTran assumption, is if you put the light source below the plane, and of course there are infinite optical thicknesses at the horizon, and that's not so. So no, this was one of the major selling points for me. I was not going to be happy until I had a spherical shell atmosphere. Now the aerosol modeling here is very simple for my usage.
Go ahead.
Yes.
So in different environments, you got aerosols that are different sizes. And
Yeah.
they scatter light differently. So how does this change for climate? Different climates.
My quick and dirty solution to that is to use the local aerosol data measured by AeroNet and say, look, I'm going to say for a later day what are the constituents of this total spectral optical depth, but I will be glad just to have that spectrum of optical depth data close in time and close in space to my measurements as a starting point. All I'm saying, I don't know what the internal workings of the aerosol species are that give me that spectrum of aerosol optical depths, but that's what I'll use in the model. You have an option to just simply put in a given angstrom coefficient and the scaling factor that lets you reproduce that curve. So I'm using the aerosol here as a bit of a black box. I've used, believe it or not, both at the Academy and inland in Pennsylvania, a rural aerosol is appropriate based on my reading. But these are very early days. I mean, I'm just so pleased to be able to explain the thing that was confounding me is how come adding any aerosol spreads up one horizon and makes the other look good? How does that work? Well, I have a sense of that.
John?
Have you done any modeling with partly cloudy conditions?
Oh God, please. I get into so much trouble just with an absolutely pristine sky that I tremble at the thought of getting more real than that. There are some fun things, though, that you can, as an observer, look for. Has anyone ever heard the term crepuscular rays? Cloud shadows. That's what those are. And you see this, one of my other, when I'm not busy torturing hyperspectral systems, is to take time-lapse photographs of twilight. And think about it. The sun is not only setting, it's increasing in azimuth. So if there are clouds that you can't see below the solar horizon, what will those produce? Those will produce rotating patterns of crepuscular rays. It's sort of a cloud version of doing a stadium wave. I mean, it's absolutely fascinating. I had a reviewer object that this is obviously a fake because it can't possibly behave like that. I said, no, the geometry is very simple. If you've got clouds that are in one place and the sun's moving behind them and you can't see the clouds, you'll get rotating shadow bands in the sky. So I'd love to, but my plate is so filled with, I can't even get the aerosols much more than penciled in.
It is curious that you didn't have any clouds in these, and I also didn't see any contrails. So this must have been a very patient set of.
Well, I showed you some of my nicest ones. No, as you well know, those of you who've done any experimental work in going to a site, you get your rig all pulled together, you get to the site, and the weather doesn't cooperate. Either the simple case is where it absolutely doesn't cooperate, but generally you try not to leave home if that's the case. But if you get there and, in twilight, the clock is moving fast, and you have to say, okay, do I want to spend the next 45 minutes watching the sky start to cloud up? So you can't, there are pictures which, some scans which have some clouds in them, but the effects seem to be minimal in the sense that there are no discernible or spectral or colorimetry changes, jumps, or shifts in the vicinity of clouds. The direct illumination is pretty weak at that point. So.
And what about polarization?
I've done some polarization imaging with fisheyes. That's great fun. The dynamic ranges are killers, though, because you have a very bright solar horizon where there's minimal polarization, maximum polarization about 90 degrees from the sun, and then some other polarization patterns that you're really interested in on the anti-solar sky. Getting that all properly exposed in a single, not single photograph, but a quartet of photographs, some of which have polarization intensity reductions that are quite pronounced. The dynamic range problem for the imaging system is a problem there. But yeah, I'm glad to show any of you some polarization maps I've done in Twilight. That's good fun.
Scattering generally decrease the polarization contrast, or multiple scattering?
Yeah, yeah. A haze overcast or a cirrus overcast. Sure, you can see polarization patterns in the cirrus, but the reason that the clear sky holds some attraction is we entertain the fiction that there's a single unifying scattering mechanism, geometry that we can invoke, and the more clouds, the more fun, but the more complicated, to the point that you can't really say that you have a hope of satisfactorily modeling it.
Any questions? Okay, let's thank the speaker again. Cookies and drinks. What's that?
A window seat, please.
Cookies and drinks out, and you can mingle a little bit, and we'll bring the speaker out.